So in section 3, we're going to talk about significance tests for population mean. So we talked a little bit about confidence intervals when we talked about proportions, but they are actually better with population means. And that's because confidence intervals and significant tests for population proportion are based on z-values. But population means uses a t-distribution with n-1 degrees of freedom. Unless we, in the very rare case, know the population standard deviation. So we learned how to do confidence intervals for a population mean in 8.3. So now we'll talk about significance tests for a population mean and then look at how that relates to our confidence intervals. So we're going to start with an example about a company claiming to have developed a new AAA battery that lasts longer than its regular AAA batteries. Based on years of experience, the company knows that its regular AAA batteries last for 30 hours of continuous use on average. An SRS of 45 new batteries lasted an average of 33.9 hours with a standard deviation of 9.8 hours. Do these data give convincing evidence that the new batteries last longer on average? So we're going to break it down just like we did in section 9.2. So we're going to start with defining our hypotheses. So our null hypothesis is going to be that our mean is equal to 30, and our alternative is going to be that our mean is greater than 30. So our null and our alternative hypothesis have to be based on the population, just like it was for proportions, and then we use our sample to make a conclusion. So just like when we talked about tests for a proportion, we still have to look at those same three conditions for a test for significance. So those are random, normal, and independent. So just kind of as a refresher, a population mean, our sample, is normal if our sample size is greater than or equal to 30. Okay, so we often won't know whether the population distribution is normal, but if the sample size, which is greater than or equal to 30, we can carry out a significance test. But if the sample size is small, we have to examine our data for any obvious departures from normality, such as skewness and outliers. We can do this by looking at a graph of our data or looking for outliers using our 1.5 IQR rule from a few chapters ago. So let's just double check that our sample meets our conditions. So we're going to start with random. Well, we're conducting an SRS, which is simple random survey, so it is random. Next, we're going to look at is it independent? Well, each battery has an equal chance of lasting longer, so it is independent. And lastly, we want to check to see, is it normal? Well, our sample size is 45, which is greater than or equal to 30, so yes, it is normal. So we have met all three conditions. If we didn't, let's talk about what we would look for. So the only condition we're likely to not meet is the normal. Sometimes we're not going to be given a sample size that is greater than or equal to 30. So we need to look to see if there's anything obvious about the problem that makes it not normal. And if there isn't anything quite obvious about it, we can go ahead and run the significance test anyway. And we'll take a look at this later on in a couple examples. Okay, so let's go ahead and talk about our formula. So at top here, we just review the definition for a test statistic that we covered in section 2, where we take the statistic minus the parameter and divide by the standard deviation. Now for a mean, we actually use a t-test statistic because we're always going to do n-1 degrees of freedom. So we'll do x minus the mean, x bar being our sample mean, minus our population mean, divided by the sample standard deviation divided by the square root of n. Okay. After we use this formula, we can calculate our p-value. Now, one of the things we ran into using our t-table was that our n-1, we didn't always have a value on there that matched, so we would always have to round. So instead, we're going to go ahead and use our TI calculator to help us get a more accurate p-value. Now, if our table contains the value we want, we can go ahead and use it, but otherwise we're going to use the calculator. So let's go ahead and find the test statistic and the p-value for our battery example. So let's go ahead and identify our information. So x bar is going to be our 33.9. Our mu naught, that's our 30. Our sample standard deviation is 9.8. And n is 45. So we'll have t equals 33.9 minus 30 all over 9.8 divided by the square root of 45. So go ahead and use our calculator. And we end up with a t-value of 2.67. So let's go ahead and draw our curve. So we are going to look for a t critical value. So that t critical value we're going to use is going to come from that t-table. So at the top, because we aren't given a level of significance, we're going to use 0.05. So at the top, our upper tail probability is going to be 0.05. Now the t critical value we're going to do, along the left, we're going to find the closest degree of freedom for our data. So n is 45, so our degrees of freedom are 44. The closest on our table is 40. So we take 0.05, we go down to 40, and that's going to give us our t critical value, which is 1.684. We're now going to determine, does our t value fall within our shaded region? And that's going to help us determine whether or not we reject or fail to reject our null hypothesis. So 2.67 is greater than 1.684. It is going to be in our shaded region. So when it asks us, would you reject the null hypothesis? The answer is yes. We are going to reject the null hypothesis. So what would be the conclusion? So we would say there is evidence to show the average battery life is more than 30 hours. So we're going to take a look at one more example. So we have that the level of dissolved oxygen, which we're going to abbreviate DO, in a stream or river is an important indicator of the water's ability to support aquatic life. A researcher measures the dissolved oxygen level at 15 randomly chosen locations along a stream. Here are the results in milligrams per liter. So we have our 15 results. A dissolved oxygen level below 5 milligrams per liter puts aquatic life at risk. Is there evidence at a level of significance of 0.10 that the aquatic life is at risk? Okay. So we're going to start with our hypothesis. So our null hypothesis is going to be that the mean is equal to our 5 milligrams per liter. And our alternative is that it is less than, because anything below that puts the life at risk. So now we're going to go through our checklist. So random, independent, and normal. So we are going to go through and actually, I'm going to write these out. So is it random? And the answer is yes. We are choosing the 15 random locations. Is it independent? And again, yes. Now, is it normal? So this is where we run into a problem because we only have 15 locations, so it is not normal. So what we're going to do here is we're going to take a look at the graph that we're going to get. So if we draw a short little X and Y axis here, we go through our values, which I'm going to kind of round just because I'm going to do a histogram just because it's so we'll 2, 3, 4, 5, 6, and 7. So if we want to first check the number of values between, then we'll do our y-axis. These are the number of values that are in that range. So the number that are between 2 and 3, there's only one, 2.87. Okay. Then between 3 and 4, there's also only one, the 3.29. Then we have between 4 and 5. And we have 4.53, 4.13, 4.83, 4.4, 4.01, 4.66. So we have 6 values. So I'm going to have to go up one more here. Okay, then we're checking between 5 and 6. We have 5.04, 5.23, 5.5, 5.42, 5.73, and 5.5. So we again have 6. And then lastly, between 6 and 7. And we have 1, the 6.38. So if I look at what this graph looks like, drawing a curve that goes along with it, my curve is roughly normal. So we can go ahead and perform our hypothesis test. So what we need to do now is use our sample to find its mean and standard deviation. So what we're going to do is go into our calculator and go into our list, and under list 1, we're going to type in all of our values. After we're done with that, we're going to hit stat again, go over to calculate, and then one variable stats. That's going to give us our X bar, our sample mean of 4.77, and our sample standard deviation of 0.94. And N is still 15. So now we can go ahead and calculate our T statistic. So we're going to do 4.77 minus 5 all over 0.94 divided by the square root of 15. So we get T equals negative 0.95. So now we're going to draw our normal curve. Okay. And we need to calculate our t critical value. So we're talking about falling below, and our alpha is 0.10. So to figure out our t critical value, we need to know our degrees of freedom. So 15 minus 1 gives us a degree of freedom of 14. So in our t table, we find our upper tail probability, 0.10. We go along this side, we find our degrees of freedom of 14. And we're going to have a t critical value of negative 1.345. We can make our t critical value negative here because we are talking about being below for our alternative hypothesis. So now the question is our t-value negative 0.95 within our critical region? And negative 0.95 is not less than negative 1.345, so it is not, which means we fail to reject our null hypothesis. So we'll take a look at some more examples over this. We're going to talk about some two-sided tests, but let me know if you have any questions about significant tests for population mean so far.